Hello, I'm Mark Finean from the Oxford Robotics Institute, and I'm very pleased to present our paper entitled Where Should I Look? Optimized Gaze Control for Whole Body Collision Avoidance in Dynamic Environments. In our work, we have been using a Toyota human support robot as a research platform, which has a holonomic base and a head-mounted depth camera that we aim to use for collision avoidance. However, we encounter the problem shown on this slide. During execution, one can easily end up traveling in a direction that the head camera is not looking in. This emphasizes the need to control the head camera. We implemented various simple methods such as panning or always looking in front and found them to be unsatisfactory in collision avoidance, leading us to develop this problem that we've called trajectory constrained active gaze control. Given our current observation and understanding of the environment around the robot, to achieve a task we perform motion planning and determine a robot's trajectory. However, all along this trajectory we have the additional degrees of freedom associated with the head camera, offering us an opportunity to both optimally observe the environment as well as provide effective observations for collision avoidance. While our paper firstly details this problem, we also describe our proposed method. Using a voxelized representation of the environment suitable for parallel processing on a GPU, we allocate rewards to each region of space. Based on the robot's currently planned trajectory, we sweep out the voxels that will be occupied over the course of the trajectory and allocate rewards for observing these voxels, providing a greater reward to those that will be occupied soonest. This enables us to provide effective collision avoidance by promoting the observation of space that we are going to move into. We additionally reward the observation of voxels that have not recently been observed or previously observed at all, promoting both exploration and reobservance of regions in a dynamic environment, since we can't guarantee that these regions will consist of free space throughout time as we can in a static environment. We then consider numerous head camera motion primitives and their corresponding projected cones of vision. For each cone, we sum the rewards and greedily select the motion primitive, or sensor pose, with the greatest total reward. We then execute and iterate this process. We implemented our method in both 2D and 3D environments and compared it against three benchmark approaches: constant head position, panning, and a fixed look-ahead approach. In the experiment shown here, the robot was given a goal state, while a dynamic obstacle continuously moved into the robot's planned trajectory. In this instance, our optimized head behavior was the only one to result in a collision-free trajectory. Across numerous 2D and 3D environments, we demonstrate that our method outperforms the benchmark approaches. The figures shown here highlight our method's ability to outperform in 3D environments in respect of both its ability to explore the local surroundings as well as in providing a superior success rate of finding collision-free trajectories. Additionally, we verified our findings on a physical Toyota human support robot using a GPU-accelerated perception framework. In this task, a dynamic obstacle was moved into the robot's trajectory while trying to reach and pick up a spray bottle. Using our method, the robot was able to successfully complete the task. It did this by continuously re-optimizing its head behavior, observing the environment, and replanning its whole body trajectory. To conclude, this work introduced the problem of trajectory-constrained active gaze control and optimizing sensor poses over the course of a trajectory for providing effective collision avoidance. We have proposed a novel solution using a greedy optimization approach with voxelized rewards and motion primitives, and we have demonstrated its effectiveness in 2D and 3D environments. Thank you for watching, and please feel free to check out our paper and reach out to us if this work is of interest to you.